Hey, good afternoon, folks. I hope all of you are doing well. We're continuing the discussion of whispering gallery resonators. So just a quick reminder or where we ended the last lecture. We're starting today with discussion of the various modes inside of these whispering planar geometry whispering gallery resonators, like the ones that are shown here that you can fabricate in a variety of materials in planar configuration. And then later today and next week, we'll talk also about ultra high Q whispering gallery mode resonators, such as microspheres and microtoroids, which have additional surface treatment steps. So today we will continue the derivation of the electromagnetic field profile inside of these planar resonators and see a variety of applications for these systems, and then move on to ultra high Q resonators. So where we ended the class last time was the introduction of two approximations that we will use in order to find analytical solution for modes of microdisk. And those two approximations are whispering gallery mode approximation and effective index approximation. Whispering gallery mode approximation allows us to neglect the fields outside of the disk. And we discussed last time that this holds when you are studying modes with large azimuthal number M. And in geometrical optics picture, azimuthal number means the number of reflections that mode makes from the interface, but you will see that in actual wave equation solution for whispering gallery modes, mode M corresponds to number of nodes. Actually, 2M corresponds to number of nodes or antinodes of the field as you're moving along the edge of the disk. So whispering gallery mode approximation means that for large M, you can neglect the field outside of the structure. And that's easy to see from the total internal reflection argument, because for large M, you have large angle of incidence of the mode relative to the interface. And the other approximation that we are making is effective index approximation that allows us to solve two-dimensional structure instead of three-dimensional structure of finite thickness. So instead of solving this disk with thickness D and refractive index ND, surrounded by refractive index N naught, we're just solving a slice of an infinite length of a cylinder with effective index N effective, same radius, surrounded by the same refractive index. So the thing that you change is basically a refractive index of this material, of this cylinder. And we're primarily interested in TE modes of these infinite cylinders, which would correspond to TE-like modes of these slabs. TE modes of cylinder means that you only have transverse values of electric field. If you consider Z is the direction of propagation, you would have only EX, EY, and HZ, magnetic field in the Z direction. And that category of modes would be used in effective index of approximation to analyze TE-like modes of this slab. And TE-like is defined in the same way as we defined it for photonic crystals, means that at the central plane, you have only TE, meaning you have EX, EY, and HZ. And then as you move from the central plane, you of course have all of the field components, but the dominant ones are for the TE modes. So TE-like is again vertically even mirror symmetry, or at the central plane TE. Of course, you can design disks for TM modes, TM-like modes. We will actually focus on TE-like because that's what's mostly used, also in optics, and all of the derivations that I'll present today are for TE-like modes. So again, whispering gallery mode approximation, neglect the fields outside of the disk, and effective index approximation means that you analyze two-dimensional instead of the three-dimensional problem, but you have to introduce effective index. And for this first order mode inside of this slab, and that's the vertical profile inside of the slab where you made a disk, you can find effective index using this set of equations. And clearly effective index is between the index of the disk and index of the cladding, and depends on the confinement factor of the mode, which in turn depends on the omega k, on the relation for the particular mode, dispersion for the mode. You can directly use these equations and plug them in for all the problems that you are solving in this class or in the homework, because we're focusing only on this fundamental mode in the vertical direction and TE-like modes of the disk. So as an example, this was the last thing where we stopped last time. As an example, if you have a semiconductor microdisk with refractive index of 3.4, which would correspond to something like indium gallium arsenide phosphide, and it's surrounded with air. That means that N cladding is 1, and G is 3.4. Let's say it's 220 nanometers thick, D is 220, and you're interested in finding, again, effective index for the operating wavelength of 1550 nanometers, which is also important to take into account because dispersion and confinement changes as a function of wavelength. You can go back to this system of equations, calculate from D, lambda, and indices, this factor V. Then from that, you calculate confinement factor. And from confinement factor, you can find this weighted average of the effective index. And for this first mode, in first order mode, you will find that the effective index would be 2.7. So instead of solving three-dimensional disk with refractive index 3.4 surrounded by air, and with this particular thickness at the wavelength of 1550, you can just solve a slice of the infinite cylinder, which has refractive index of 2.7. And if you are interested in the same disk operating in some TM-like mode or a higher order TE-like mode, or at a different wavelength, you will have to recalculate effective index. And keep in mind that these equations only hold for the mode that would vertically have this particular profile. Okay, so we'll go back to this effective index of 2.7 again today when we're solving for whispering gallery mode profile. So keep in mind that this is for a specific set of parameters that we picked, but we picked it by keeping in mind that we would like to actually this system to operate in the single mode regime vertically. This thickness of 220 nanometers is again something that allows you single mode operation for the TE-like modes. Same set of thicknesses we've seen for photonic crystals. And 1550 is, of course, the desirable wavelength for operation in photonics because of the minimal losses in fibers. So knowing all of this, what we can do now is we can go back to our approximations and solve the problem analytically, right? So this is the new thing now. So in assuming whispering gallery mode approximation, that means that you can neglect all the fields outside of the disk. Of course, that's not true in real life because there are evanescent fields outside of disk and you use them to couple evanescently from a fiber taper and so on, or couple between waveguide and the disk. But we can assume that this vanishes if we're solving for large azimuthal numbers M. And that would still give you a very accurate field solution inside of the disk and correct values of the frequency of the mode, meaning wavelength and field pattern and so on. But you, of course, have completely inaccurate field profile outside of the disk. Nevertheless, in whispering gallery mode approximation, if you assume large M and you neglect the fields outside, that would also mean that you have boundary conditions to solve your problem, which tell you that field outside of the cylinder vanishes, and also at the actual surface of the cylinder, field would vanish. So you can write that your magnetic field will be equal to 0. And keep in mind that we're solving for TE-like modes or TE modes of a cylinder. So for TE modes of the cylinder, there are electric field components in plane, EX and EY, and magnetic field along the axis, Z-axis. So since there is only one component of magnetic field, it is much easier to solve for magnetic field, right? So you deal only with HZ. And that's why I'm writing wave equation for magnetic field. So you have this infinite cylinder, right? And inside of this cylinder here, you have only HZ, right? And practically when we solve for magnetic field inside of this infinite cylinder, that would correspond to solution of magnetic field at the central plane of this disk, right? We won't have solutions away from the central plane, but in many cases, you only care about the central plane because that's where your quantum well would be, or that's where most of the interaction would happen. So to write equation for magnetic field, wave equation for magnetic field, you basically just write it inside of this uniform medium with effective index and effective, right? And you have boundary conditions that HZ component of magnetic field, which is only non-zero magnetic field component, drops to 0 at the surface of the disk, and it's 0 outside. And that's what we did here. We just write very simple wave equation, basically Helmholtz equation for uniform medium with refractive index and effective. We wrote it for a monochromatic field with frequency omega. Refractive index is N effective inside. And we write it in cylindrical coordinates because that's the most natural geometry to solve the problem. and Laplacian in cylindrical coordinates is given here. Okay, so now you have only one magnetic field component, right? You have to solve it in cylindrical coordinates. This is for monochromatic solution with a particular frequency omega, which is why you have omega here, and refractive index is n effective everywhere. We can write magnetic field as the product of something that depends on space and e to the I omega t, which is time dependence. And here we only write magnetic field as a function of r and phi, because we're assuming that there is no really dependence on the z coordinate. We're not really, of course, you can solve for the modes that are propagating along the axis of the waveguide, but that's not what we're solving here. We're just solving a two-dimensional problem, meaning it's a non-propagating mode. I guess it would be mode that has no z dependence at all. It would be cut off for the waveguided modes. And those are the modes that we're interested in because we're representing in effective index approximation, three-dimensional problem with two-dimensional problem. So when you go back to your spatial dependence on magnetic field, you can try to separate variables and represent it as a product of something that depends on radial coordinate and angular coordinate phi. And you plug that back into the wave equation and try to separate variables and solve the problem. And when you do that, you can separate variables indeed, and you will obtain two equations, one that depends only on r and one that depends only on phi. And you can group them on two different sides of the equation and write that both of these are equal to constant, which we will label as m squared. And it was labeled as m squared on purpose because it will turn out that this m is the same as the azimuthal number m that we had before. And the second equation, at least, that emerges here for the angular dependence is pretty simple to solve. This equation basically just tells you that you have solution for this angular dependence, which is e to the I m phi. Right, because the second derivative is just equal to minus m squared times phi. So it's a simple e to the plus or minus I m phi dependence, where m emerges as this azimuthal number, because you'll see in a moment it also represents number of nodes or antinodes that you will have around the edge of the disk. The other equation that we have is a little bit more complicated, but it also has analytical solutions. So we'll go back to that later. And before I actually show you the solution, I'd like to emphasize, and I'm going through this quickly because you've probably seen this problem before. If you solve the problem such as cylindrical nanowire in quantum mechanics, or if you solve modes of a fiber or any cylindrical geometry problem, either Schrödinger equation or wave equation, you've seen basically this solution. It's exactly the same solution because we're solving wave equation in a cylinder, right? So that problem emerges many times in physics. Okay, so going back to the angular dependence, the solutions are e to the plus or minus I m phi. Since we're looking into something, so solutions in steady state, then actually that implies that this phi has to be periodic with periodicity 2 pi. Because the pattern has to be the same when you make the full cycle around the edge of the disk, which means that m has to be an integer. If m was not an integer, then phi of phi and phi of phi plus 2 pi would not actually be the same. And this m is the same as the azimuthal number that we introduced in the picture, ray picture before. So we'll see in a moment how it influences the pattern of the field. The other equation that we have is this equation here for the radial part of the mode. That equation also has an analytical solution. And as probably many of you already know, this equation has solution, which is a superposition of Bessel functions and Weber functions. But since Weber functions actually go to infinity as their argument goes to 0, that's not really physical here. So we drop off the Weber function term because it would mean that electric field would go to infinity at the central axis of the disk, and that doesn't really make sense. So we just take Bessel functions as a solution to the problem, and the whole solution would be the product of the Bessel function and this e to the I m phi into the minus I m phi part, right? So here is the whole solution. Magnetic field, and that there is only z component of magnetic field, would be product of the radial part of the solution and angular part of the solution. Radial part is the Bessel function, and the angular part is e to the in phi. And there are two solutions actually for the same radial part. You can have e to the plus in phi and e to the minus in phi, which are two degenerate solutions. And we'll see how we handle that in a moment. So for the radial part, it is a Bessel function, and we labeled it with two arguments. And this is because it also depends on some other additional parameters that we will derive from the boundary conditions in the system. But we also label the actual Bessel function. I mean, it's also here visible here that the Bessel function order depends on the azimuthal number m. And that's because of the equation that we were solving, just to go back to that, since I very quickly went through that. For the radial part, we're solving this particular equation, and the same number, m, that we had in solving the angular dependence is used here after the separation of variables, and that influences the order of the Bessel function. But the argument of the Bessel function depends on this argument a, and that argument a, if you kind of look at the connection between these two equations, depends on effective index and frequency of the particular mode. So when you go back here and write the whole thing, order of Bessel function depends on the azimuthal number, the same argument that goes into the angular dependency to the in phi, but the argument of the Bessel function depends on the effective index and frequency and radial position and speed of light. And I also introduced another argument here, n, that's referred as the radial number of the mode. And I used it to label frequency. And the way this radial number of the mode emerges here is from the boundary conditions that we haven't used yet. So we'll see in a moment how this creates the radial pattern of the mode. But again, you may have also seen it from other cylindrical geometry problems that you have had before. And while the azimuthal number of the mode gives you the number of nodes and antinodes that you have as you travel along the edge of the disk, the radial number of the mode would give you the number of nodes that you have in the field as you go from the center to the edge of the disk. So for particular radial number of the mode n, you will have n-1 zeros of this function describing the field as you go from the center to the edge of the disk. And that will be clear in a moment, actually, when we start plotting the field based on these equations instead of just going through the math. So how do we use the boundary conditions? The boundary condition that we have is the one that we derived from the whispering gallery mode approximation, which tells you the field outside of the disk is 0, and also tells you that the field component, hz, at the edge of the disk is 0. So that means that this magnetic field for r equal to rho, which is the radius of the disk, has to drop off to 0. And since the last part doesn't depend on r, and this is just a constant that we introduced up front, which gives you the magnitude of the mode, that means that this Bessel function has to drop off to 0 when r is equal to rho, the radius of the disk. And from that, you can actually find frequencies of particular modes. In other words, this argument here, in order for Bessel function to be equal to 0 when r is equal to rho, that means that for this particular argument of the Bessel function, when you plug in the radius of the disk, would have to be equal to 1, 0 of the Bessel function of the order m. So for example, if you set that this whole argument is equal to nth 0 of the Bessel function jm, which we label as SMN, that means that would basically allow you to find the frequency of that particular mode, right? So SMN is nth 0 of the Bessel function Jm, and that has to be equal to the argument of the Bessel function when r is equal to rho, which allows you to find the frequency of a particular mode. So these two arguments are clearly important to keep track of, because one is giving you the azimuthal number of the mode, and the other one would give you the radial number of mode or the number of zeros in the radial direction, and that comes from your choice of a 0 of a Bessel function here, right? Because you can cut it off at first 0, second 0, third 0, and so on. Any questions about this? I mean, we'll go through the example later on. I'm just quickly going through math, but it will be clear what is going on when we plot the field based on all of this. Okay. Any questions? If not, let's keep going. to more interesting parts. So if you look at this equation here that we have for frequency, you can also represent it in terms of wavelength, because of course this is 2 pi c over lambda, where lambda mn would be wavelength of the particular mode labeled with indices m and n, azimuthal and radial numbers m and n. And for that particular mode, the relation would be given here, which tells you that if you go to higher order zeros of Bessel function, ratio between radius and wavelength would be increasing. And this is expecting, this is just telling you if you go to higher order TEMN modes, right, which have larger azimuthal and radial numbers, then the wavelength of the mode would get smaller and smaller relative to radius of the disk, okay? So higher order modes will have basically a lot of nodes and antinodes within the disk, but we'll also have wavelengths that are getting smaller and smaller comparable to radius of the disk. So fundamental modes, lowest order modes would have wavelengths comparable to the radius of the disk. And then as you're going to higher order modes, their wavelengths would be smaller and smaller comparable to radius of the disk. Or in other words, if you would like your system to operate at the wavelength of 1.5 microns, right? And you make the disk that has a radius comparable to that wavelength, then you are expecting the system to operate probably in some very low order mode, low m and n numbers. But if you would like the system to operate in a very high order azimuthal number mode, or large m and large n, it's clear that you will have to make disk with a radius rho, which will be much larger than the wavelength, because this zero will also be some large number, right? This zero of the Bessel function would be a large number. Okay, so I mentioned that there are two possible solutions for the angular distribution, right? So for the radial, there is one solution, which is the Bessel function, and for the angular, there are two solutions, plus and minus m. And if you go back to the equation, for the angular part, it's clear that e to the plus im phi or e to the minus im phi, they're both solutions. So you can, that tells you that there are two degenerate modes, right? You can write the product of the Bessel function and e to the im phi, or Bessel function and e to the minus im phi. So those are two different solutions, right? And they're degenerate. They have the same, exactly the same frequency, because they correspond to the same SMN, same zero of the Bessel function. Instead of using e to the plus im phi and e to the minus im phi, you can also use sum and difference of these two, right? Because the radial part is the same for both, but the angular part is different. So I can either work in the propagating basis e to the plus minus im phi, or I can work in the basis where I add them and subtract them, which is a standing wave basis. So e to the im phi plus e to the minus im phi would give you cosine m phi, and minus sign would give you sine m phi, right? So in either basis, you have two degenerate modes that have the same radial distribution, but they're either represented with standing waves that are offset a little bit relative to each other along the edge of the disk. So that would be cosine m phi and sine m phi. Or you're working in the basis, propagating basis, where you have this e to the plus or minus im phi times omega t, which is a mode that travels around the edge of the disk with some angular velocity. Which basis you use to solve the problem? So one mode, of course, would go in the clockwise direction, and the other would go in the counterclockwise direction, in angular direction, because it's e to the plus or minus im phi times e to the I omega t. So which basis you choose to solve the problem depends on the problem that you are solving. If you have your quantum emitter atom at a specific location, and you're just interested in looking at the interaction of an isolated disk with that quantum emitter, then you will pick standing wave basis, right? And one of these modes maybe both of them, or maybe just one of them would be coupled to that particular mode. Or if you are interested in coupling to that disk from outside, from a propagating mode of a waveguide or a fiber, as we'll see in a moment, then you would prefer to work in a propagating mode basis, because you may be able to launch only to clockwise or counterclockwise mode, depending on how you're exciting the system. It really doesn't matter, both bases are equivalent. You just pick the one that works better for your problem. The most important part is that for any combination of azimuthal and radial number, m and n, there are two degenerate modes. And one corresponds to plus m, the other to minus m, or cosine m phi sine m phi. So now let's go back to our problem and see how that all applies to solving the field for one specific system. And I will pick exactly the same system that for which we calculated effective index, right? So remember, we found that effective index of 2.7 would correspond to a disk of thickness 220 nanometers with refractive index 3.4 operating at a wavelength of 1550 nanometers, okay? So let's say you're asked to design a disk of thickness 220 nanometers. Typically, you don't have a choice over thickness, right? Because you purchase a wafer from a company and it's indium gallium arsenide phosphide on insulator. It's 220 nanometers thick, so you're stuck with that. But you know that you want to build a system that specifically operates at 1550 nanometers. Maybe you're building a laser for some fiber optic communication system, so you want to actually have 1550 nanometers operation. That's where your quantum wells are. Thickness is 220 nanometers. Operating wavelength is 1550. You know refractive index of indium gallium arsenide phosphide, and that wavelength is around 3.4. So you find the effective index of 2.7. Okay, so we already found that. But now the question for you is, you know that you want to build a microdisk laser, right? And you would like it to operate in the mode 16.1, right? I mean, this is choice of this, the combination of numbers can vary, right? There are, of course, a lot of different modes, but let's say you would like it to operate at the mode 16.1 at the 1550 nanometer wavelengths. Generally, you would like it to operate in n equal to 1 mode. And there are multiple reasons for that, because n equal to 1, as you'll see in a moment, means that you have only one lobe in a radial direction. And those modes have the smallest mode volume. It will be easiest to couple to them from the outside and so on. So there are many reasons for that. But you have some flexibility over this number m. I mean, if you don't hit m equal to 16 mode with particular diameter, maybe you hit 17 or 20 or so on. So for n equal to 1, m equal to 16 mode, the magnetic field distribution would be given here. So this is what we just found. And here I picked to work in the standing wave basis, right? So let's say I pick cosine of 16.5. You can also write sine of 16.5, doesn't matter. It's just a rotation relative to cosine mode. And radial part of the distribution is just a Bessel function, right? And with the argument that is given here. So effective index, which we found is 2.7, R is the radial coordinate, and omega 16.1 is the frequency. And omega 16.1, the frequency of that mode, we know could be found from this expression. This is what we had derived from the boundary conditions, from the fact that this field here has to exactly drop off to 0 at the boundary of the disk, which is radius equal to rho, right? So for 16.1 mode, you pick 0 of the Bessel function J16, first 0 of the Bessel function J16, okay? That's S16.1. So omega 16.1 is given by this expression, and you can also plug that back in here, right? And cancel out different terms, and that would basically give you just the argument, which is R divided by rho times S16.1. And it's clear that when R is equal to rho, when you hit the edge of the disk, then this whole argument is just S16.1, which is first 0 of Bessel function J16, so that whole Bessel function drops to 0. Just to make this clear, let's just plot the Bessel function J16. This is how it would look like, right? So what are we doing here? If you say that you would like your system to operate in the mode 16.1, right? Then you have to plot Bessel function J16, because that's the function that defines the radial dependence of the mode. But if you pick radial number of 1, that means that you will truncate this Bessel function at the first 0 here. And S16.1, first 0 of Bessel function J16 is 21, right? So this argument would be 21. If you, for example, say, I would like this laser to operate at mode 16.2, you would truncate Bessel function at the second zero, sorry, here, right, which is around 26. So then, that case, you would take S16.2 here as the argument, which of course would change the frequency of the mode. I mean, frequency is fixed because of the wavelength that is fixed, but that would, in this case, when you are designing diameter of the disk, change the diameter of the disk relative to wavelength of 1550 nanometers, which is your target wavelength, right? So for the 16.2 mode, you would truncate it here at the second zero. That would give you a very different radius of the disk if you would like to specifically operate at 1550 nanometers. But it would also mean that as you're going in the radial direction of your microdisk, you are going to see two lobes of the field, right? There would be the first ring, first lobe, first ring, and then second ring. And likewise, if you operate at TE16, whatever, 5 mode, then you will truncate it at the fifth zero. So you would see 5 rings of the field in the radial direction. Does that make sense? Okay, I hope it does. I didn't see any, I hope no feedback is good feedback. Okay, good. So that's in the radial direction. We see number of lobes that are given by your choice of the zero Bessel function where you're truncating. And that also tells you why we call the number n, which is the order of the zero, which you pick in the Bessel function, why that number n gives you the radial number. I said earlier on that radial number n means that you have n-1 zeros of the field in the radial direction. So if I truncated the first zero, I will have no zeros, no intersections apart from the one at the very center, but we don't count to that one. So I will have no zeros of the Bessel function in the radial direction until I reach the edge of the disk. If I pick the second zero, I will have one actually zero of the field as I go in the radial direction between the two rings of the field, and so on. So you can view radial number as the number giving you number of zeros of the field, or in other words, number of rings of the field for whispering gallery mode that you will see in the radial direction. So n equal to 1 means 1 ring, n equal to 2 means 2 rings, n equal to 3 means 3 rings because you truncated here, and so on. Okay, and that also tells you preferably want to operate in the n equal to 1 modes because only 1 ring means smallest mode volume. There is no field in the center of the disk. And there are also other reasons, you know, remember how these disks look like. They have a pedestal holding them on at the center. So if there is a pedestal holding it on in the center and you operate in a mode that has higher order n, radial number, that means that these inner rings interact with the pedestal and they would have lower Q factor. Right? So that's another reason why you don't want to operate in those rings, in those higher order modes. And that's also the reason why we typically go to ring geometry instead of the disk geometry to fix that problem. So going back to our 16.1, TE16.1 mode, right? I know that this is the radial part. I plugged in directly my zero of the Bessel function, first zero of Bessel function J16, and then the angular distribution is just cosine 16 phi. So when you put all of that together, right, I expect my field to look like something that has just one lobe, one ring, before I get to the edge of the disk, which is here. So there'll be one ring of the field. And then angular distribution would be this lobe from the Bessel function multiplied by cosine 16 phi. So when you think about cosine 16 phi and plot that from 0 to 2 pi, how would that look like? How many zeros would it have? I'm sure you know that, but anyway, I'll just plot it on the next slide. So cosine 16 phi from 0 to 2 pi, right, which is one whole trip around the edge of the disk, would have basically 32 zeros, right? It would have 16 positive lobes, and positive is red here, and 16 negative lobes. And if you go in the radial direction, it will look exactly as Bessel function J16 until you get to the first zero. So nothing, 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 and then a lobe. And of course, you have to flip a sign here because of that angular distribution, right? But other than that, you always only reach first 0 and when you get to the edge of the disk. So n equal to 1 means one ring, and m equal to 16 means 16 positive, 16 negative lobes, like cosine 16 phi as you go in the radial direction, sorry, in the angular direction, or in other words, you have 32 zeros. And this is where our kind of ray optics picture connects with the wave equation picture, because when we first introduced the azimuthal number of the mode, we said, well, if you think about a ray which is reflecting from this and building some polygon, let's assume we have 2m reflections of the field, okay? And those points where you are having reflections of the field, I mean, depending on the polarization of the field that you're picking for a particular problem, but those would be exactly the points where you have zeros or antinodes of the field, right? Which is why we said 2m, not m. And that's why m defines kind of number of reflections in the ray optics picture, which is of course not accurate, but you know, for very large, very large disks would work. But here defines you number of zeros of the field that you have, right? So you have 2m zeros of the field, or m positive and m negative lobes. And in this particular case, knowing all the parameters of the system, you remember the problem that you're solving is the problem of picking diameter for the disk if you were constrained with having in-gas phosphide material with 220 nanometer thickness, and you're building a laser for 1550 nanometer operation, you would have to build a disk which has radius rho, which is equal to 1550 nanometers divided by 0.81, okay? So that's the radius of the disk that you will have to have. So something on the order of 2 microns, 1.85 microns radius exactly, right? So this, you would design the system in such a way that it operates exactly in this mode at the 1550 nanometer wavelength. Okay, any questions here?
Yeah, actually, I have a question.
Sure, yeah.
Didn't we assume the azimuthal number m to be a sufficiently large number?
Yes, and this is, of course, the larger it is, the more accurate the solution is, but m as 16 is already pretty large, sufficiently large to be in the regime where whispering gallery mode approximation holds. So you'll see in a moment comparison between this and numerical calculation, and there is a very small difference between this result that we obtained here and the result that you would obtain numerically, which means that you are already in a sufficiently large numbers range. But the larger it is, the better the match would be. So if you go to m equal to 100, it will be even be a better match.
Okay, so for a smaller number than 16, it doesn't really work, right?
There is no sharp boundary. I mean, I guess going to something larger than 10 gets to okay range, but if you are in the regime where m is like 3 or 4, it's not going to be sufficiently large.
Okay.
Yeah. So this is TEMN mode. Keep in mind, right? So azimuthal number m, radial number n, and we only solved it for TE modes, right? So this distribution of the field that we have here would be a distribution of the field at the central plane of your disk, because we introduced effective index approximation. At that central plane, you will only have EX, EY, and this component of magnetic field. So how do you find EX and EY? You can just apply Maxwell's equations and apply curl to magnetic field, and that would give you EX and EY. But keep in mind that this is at the central plane. Same as for photonic crystals. As you move away from central plane, you have all components of E field and all components of B field. But these ones are dominant for TE-like modes. So it's the same as any slab type problem. My question for you is, I mean, here we solved it for 16-1 mode. Let's say I ask you to plot the field pattern of the mode TE, let's say 25 and 7. What can you tell me about that mode? How would the field pattern look like?
Would it not be symmetric anymore?
TE 25-7, right? So what can you tell me about that mode? how would it look like, right? If this is 16, 1.
Well, 7 nodes in the radial direction and
Exactly. So there will be
27.
7, exactly. So there will be 7 rings of the field in the radial direction, right? Filling up the disk. And 25 would mean what? How many, if you go in the angular direction, how many zeros will you see?
50.
50, exactly, right. And in the radial direction, I mean, of course, this is J16, right? But if you, for example, do 16, 7, you would truncate at the 7, 0, and that would give you the number of rings. So of course, Bessel function 25 looks different from Bessel function 16, right? But you still are truncated at the 7, 0, so that gives you the number of rings, okay? They all kind of look similar. I mean, they're not too different from each other. I mean, Bessel functions. Okay, so that's how you're plotting the field. And you can also use this exercise, as we said, for you will be doing some similar problems in the homework, but also in research or everyday life, if you actually are interested in designing a disk, you can use this approach to design the disk to operate at a particular wavelength. So let's say you have a wafer and you like to make an array of disks that would operate at a variety of wavelengths. You can actually use this approach to design the system. I mean, because from this approach, you can find exactly what diameters of the disk you need to etch in your wafer so that it operates at a particular wavelength. And that's the idea. I mean, it doesn't give you the field outside of the disk accurately. It doesn't give you any field outside of the disk, but inside of the disk, you have an accurate field distribution, and it also you have pretty accurate value of the relation between the wavelength of the mode and the radius of the disk, which is what you exactly need to do in order, if you were to go to fabrication facility to etch disks to operate at certain wavelength. So just comparison to exact calculation, right? So here we went back to actual 3-dimensional problem. Thickness 220 nanometers, refractive index 3.4, right? This is what we started from when we calculated effective index. And we solved for 16-1 mode, right? And we'll talk about these numerical methods in an inverse design later on at the very end of the quarter. But when you are running numerically, you're numerically solving the problem, again, you obtain something that's normalized by the wavelength or dimension. I mean, you would obtain the relation between the wavelength of the mode and dimensions of the system, right? There are no precise dimensions. You have to just rescale them relative to the operating wavelength of the mode. So if you analyze this 3-dimensional problem without any effective index approximation, you will find that for 16-1 mode, the wavelength for 16-1 mode is related to the radius of the disk as lambda is 0.82 times rho. And that's very close to what we obtained from the approximate solution, where we found that lambda is 0.81 times rho, right? So that's related to Eubin's question. At m equal to 16, n equal to 1, you are already in a sufficiently in the regime where you can apply these approximations, both the whispering gallery mode approximations. And of course, there is some degradation coming from the fact that you apply whispering gallery mode approximation and effective index approximation, but it's not a very big degradation. It's pretty much the same as the solution that we obtained numerically. And this here gives you the actual field pattern. Actually, this is electric field amplitude for that particular mode inside of the microdisk. It's the same 16-1 mode. And this field is plotted again at the central plane of the disk. To find the field, electric field, you would have to, of course, find curl of magnetic field, find Ex, Ey, and this is magnitude of Ex. Actually, this is Ex squared plus Ey squared plotting inside of the disk. And looks very similar. I mean, there are some differences, such as the field outside of the disk, but that some of that is a result of this scattering and imperfect discretization, because this was done in rectangular coordinates and not in cylindrical coordinates, and some differences in the field inside, but more or less you actually have the right field pattern. So if you were interested in doing light matter interaction between some quantum emitter that is inside of this disk, or you were calculating lasing threshold and you know that your active material is only at the central plane, this approach gave you pretty good approximation for the field at that central plane. And you could use this analytical solution already to find either Lezing threshold or find a coupling parameter between quantum dot and the field and so on. The other actually thing that I'd like to emphasize before we make a break is that we plotted this by multiplying Bessel function with cosine 16 phi. Keep in mind, again, what we emphasized before, that there are two solutions that are degenerate. One is cosine 60 phi, the other is sine 16 phi, right? Or cosine m phi, sine m phi. So how would the other one look like relative to this one? If this is the one that we plotted for cosine 16 phi, the other one would look how? Just rotated, right, slightly, right? So it would have maxima where the other one has zeros and vice versa, okay? So those are the two degenerate modes and they have exactly the same frequency. So we'll make a brief break, but then we'll talk about the quality factor, right? Of course, these whispering gallery resonators confine light by total internal reflection, and that's imperfect confinement. So even if you look at them in the effective index approximation, where you treat it as a two-dimensional problem, quality factor would not be infinite because you have a field which is, you have electromagnetic waves that are basically propagating along the edge and getting reflected and confined by total internal reflection. So there would be some loss coming from imperfect confinement, and that would limit the quality factor. So what we will do after the break is we will derive the upper limit on the quality factor, which comes from the imperfect confinement in the radial direction by total internal reflection. And that's not the accurate value of the Q factor, it's just the upper limit, but it will give you an idea of, for example, the fact that you have to make larger disks and operate in larger M modes if you were interested in building a higher Q resonator. And we'll also see some applications of these disks and rings, which are the same thing, just etch out the central part in modulators and other types of practical systems. Okay, thanks. Let's make a brief break now. folks, I think we can go back to discussing this. And before we start deriving the upper limit of the Q factor, I just wanted to use the picture from this paper to illustrate a few points that we made previously. So this is a paper from Caltech Oscar Painter's group, where they looked at the transmission through microdiscs, and these are 10 micron microdiscs in silicon. And important development of this paper is that they showed that they could improve Q factors by treating surface of the microdisc with some specific treatments and chemicals in order to increase the Q factor, because they turned out that most of the limit on the measured previously on the Q factors of silicon microdiscs was coming from the absorption in some untreated dangling bonds and surface states that are produced at the surfaces as a result of the action. So after the treatment, they got much better Q factors of the structures. So that's kind of what is the most important development of this paper, and they measured Q factors that are approaching million. But what I wanted to discuss with you are actually these results at the bottom. So what they're doing is they take a fiber taper, actually just fiber which propagates light next to the disk, and they measure transmission through that fiber. But of course, since fiber diameter is much bigger than diameter of this disk, thickness of the disk, which is on the order of a few hundred nanometers, then they have to taper fiber so that mode in the fiber is confined in a much smaller space comparable to this thickness of the disk. And that's how they measure transmission. And if they measure transmission and tune a laser that they couple to a fiber, this is what they would see, right? So there is a fiber here positioned next to the disk. There is a laser, tunable laser at the input, and then at the output, there is a detector, and they look at the transmission spectrum, and they see this, right? So what is this? When transmission drops, this is where you hit a resonance of the disk. And you basically couple from a fiber to a disk by evanescent coupling. Of course, our B-spring gallery mode approximation would not allow us to calculate that. The reason why you have an evanescent coupling is because every mode of this disk also has evanescent tail out. So the mode of the fiber, which is positioned here, and the mode of the disk would couple to each other, and you would have transfer of the power propagating in the fiber to a disk. So whenever you hit a resonance of the disk, you would have a drop in transmission through the fiber, which is coming from the fact that you are exciting a mode of the microdisk, which can, then once you couple to the microdisk, that could re-radiate somewhere else into some radiative channels, or there may be another waveguide to which you are dropping, as we'll see in a moment in different configurations, but it would not be transmitted down the fiber, right? So that's why there are these drops. But in any case, from the drop of the power transmitted down the fiber, you can actually find the locations of the resonances of the disk, and you can also extract their Q factor. And keep in mind that these Q factors that you are measuring are so-called loaded Q factors, because these Q factors also introduce coupling between your input fiber and your disk. It's not unloaded Q factor. So the better the two systems are coupled, the smaller the Q factor would be also, right? Because you will have a lot of transfer between a fiber and the disk, but you can also extract unloaded Q factor from that system by changing distance and so on. So those are details of the experiment, but there are a few interesting things to point out, right? So here they write numbers, and first number that they write is the radial number for the mode, and the second number that they write is the azimuthal number of the mode. And because of the symmetry of the mode of the fiber that they have, they can only excite TE-like modes. They can't really excite modes. I mean, they pick specific polarization, which excites only TE-like modes that have electric field in plane. So all of these are for TEMN mode, except that N is the first number and M is the second number. So a few interesting things happen here, right? When they go to high ends, like 3, and they don't even plot it for anything larger than 3. For 1 and 2, there is no problem, right? But when they get to 3, there is a severe degradation of the Q factor, right? Much, much lower Q factors than for 1 and 2. Why is that happening? And why don't we even see the modes with N equal to 4 and so on?
Isn't it because with larger N, the mode is less concentrated at like the edge of the disc, so it's
Yes,
it
yeah,
coupled. It doesn't really couple to the fiber.
well, there is something else going on, right? And you already answered the question about the influence of n on the number of rings that you are having of the field, right? So as you go to larger number n, what you are also having field is, as you said, less concentrated at the edge, right? But it also is, you will have lobes that are going towards the center of the disc where you have a pedestal, right? So there'll be one ring here, another ring, and then, you know, as you go to a larger n, you will have rings that are interfering with the pedestal. And keep in mind that this pedestal is of the refractive index that is much higher than the refractive index of air. So you will basically have your field leak through the pedestal, right? So that is affecting the Q factor. So it's a combination of effects. I mean, I agree there is also the effect of coupling to the fiber, but the most dominant effect here would be the effect of the pedestal, which is why you'll see dramatic change in the Q factors of modes with lower n and larger n. There is another thing that is going on also, and that's visible in the picture on the right. So when they do very, very fine scan of the laser, I mean, that's not something you can resolve in this coarse scan on the left, but in the very fine scan, right, you will see that each of these big peaks split into two peaks that are separated by only something on your picometers, right? So what do you think these two peaks are, and why are they split? They have the same label, right? So that's the hint, right? Because you don't, each one of these big peaks would be splitting into something like this. So it's the same M and the same N. So let's say 32 and 1, right?
Is it because of the degeneracy?
Exactly. So it's because of the degeneracy, but of course degeneracy means that they should have exactly the same wavelength, right? But they don't. Why do? Yeah, they don't because of the imperfections in the system. I mean, there are a lot of things that can happen here. If it's not a perfect disk, there will be splitting. I mean, it could also come from different interaction with the fiber for the two modes and so on. But any asymmetry in the system would lead to degeneracy, and you will be seeing small splitting of the modes. But these two peaks are the modes that we said are degenerate in the perfect geometry. Okay. And
wait, I have a small question. So the 323 mode here, you see two peaks that are very visibly two peaks other than on the other modes. Is that just because it so happens that the 323 mode, the imperfections affect the two different degenerate modes much more differently?
it could be related to that. I mean, because these modes are, maybe there is some effect of the geometry of the pedestal where this starts kicking in for modes that have 3. I mean, because remember, for modes that have large number n, they're interacting with the pedestal. That's the problem. So I would assume that the reason why you see these low Q modes that are split by a lot has to do with the interaction of the inner ring with the pedestal. And how, I mean, pedestal is not necessarily completely symmetric. That depends on how you are etching the substrate, and that may, and is it isotropic or non-isotropic etch? So maybe it just has to do with how cosine 16, whatever, like cosine and sine modes are interacting with it. This is my guess, right? I don't know for sure because I was not involved with this work. Okay, so going back to the Q factor, we said we would derive the upper limit on the Q factor, right? And even if you go back to two-dimensional geometry, which we introduced from the effective index approximation, Q factor would not be infinite for that problem, right? And even if you go back to ray picture, right, you have your ray, which is bouncing and making 2M bounces from the edge of the disk. You have a curved boundary, right? It's not a perfect boundary. So if you look at the problem of confined beam, which is reflected from the curved boundary, it turns out that it would not, even in the total internal reflection regime, because you have some spread of the K vector whenever you have confined field. you will actually have some transmission from the curved boundary, which is occurring as a result of the fact that it's not really a single K mode and a flat boundary. It's a curved boundary and a mode that has a spread of K. So what we're going to do here is we will use this expression for a transmission of the field, or imperfect reflection that occurs from the curved boundary, and use that to derive the upper limit on the Q factor. Okay, and I'm not deriving this expression. The reference that is given in the course reader has the actual paper that this is taken from, but we will just use this expression to find the upper limit on Q. And this expression basically gives you a transmission that the field would make at each bounce from the boundary, right? So it depends on the order of the mode. So this is derived for, again, TEMN modes, and we're doing it in two-dimensional geometry. So this doesn't take into account imperfect confinement by total internal reflection in the vertical direction, just imperfect confinement in the radial direction. So at each bounce from the boundary, you will lose some fraction of the power, and that depends on the order of the mode, and it also depends on the refractive index contrast between the two materials. So this SMN is the N0 of Bessel function M, order M, or the same as the numbers azimuthal and radial number of the mode. And theta I max is the angle that defines basically critical angle for total internal reflection. So that's the angle whose, that's angle that you find from the Snell's law, right? So it depends on the refractive indices and depends on the order of the mode. So how can this allow us to find the upper limit on the Q factor? So you have a mode, TEMN, which is making and 2M bounces from the boundary. And keep in mind that actually this expression works better for, again, high order M, and works well for when N is equal to 1, right? And those are mostly the modes in which we would have our system operate. When you go to very low numbers M, or you go to N, very large numbers N, it's also not going to work very well, right? So in this picture, when you go to N equal to 1 and you go to larger M's, you're also getting closer to this kind of ray optics picture where in each bounce you're transmitting some amount of power, which is limiting your Q factor, right? So that's the loss that you will have, transmission through the curved boundary, that you will have at each of the 2M bounces, right? That's given here. And we also know that the field travels around the curved boundary, around the edge of the disk, as e to the I m phi minus omega t. I mean, it could be e to the plus minus I m phi minus omega t, which means that you have the two modes. One travels clockwise, that's, let's say, this one, and the other travels in the other direction, right, counterclockwise. But if you look at this, and here, of course, we're working in the clockwise and counterclockwise basis instead of the standing wave basis. If you look at the argument of this exponential function, you can easily see that the angular or azimuthal phase velocity, which is phi over t for this mode, or the velocity with which the mode travels in the azimuthal direction, is just equal to omega divided by m, right? So this is the speed with which the mode would travel in the azimuthal direction. Simply from the argument, treating this the same way you treat plane waves and find plane phase velocity of the wave traveling in a particular direction in space. But here, space is travel around the azimuthal, around the edge of the disk in the phi direction. So phi over t is omega over m, that's the azimuthal phase velocity. So if you have 2m bounces, right, they would be 2 pi divided by 2m apart. So the angle between two reflections is 2 pi divided by 2m, which is pi over m. So the amount of time that it would take for the wave between two bounces from the interface would be obtained by dividing delta phi with the azimuthal phase velocity. So that's pi over m divided by omega over m, and that's just pi over omega. So pi over omega is the amount of time that it takes for the wave to go from one bounce to another bounce. And I'm doing all of that because I know that at each bounce from the boundary, there will be loss appearing, which is given by this particular expression. So how do I use all of that to find the Q factor? Well, I know that energy of the mode given that is described by a particular frequency, and the Q factor would decay as initial energy times e to the minus omega t over Q, okay? So if you simply take the derivative of that would be proportional to minus omega over Q, as shown here. So time derivative of the energy, which is giving you power, would be proportional to minus omega over Q times energy. But I also know that at each bounce from the surface, the mode would lose some fraction of that energy, which is given by the transmission factor that we found before, right? So at each bounce, we will lose the energy, which is equal to Tm times the energy of in the mode. And when you look at, and of course, that decrease in the energy, which is just transmission at each bounce times the initial energy, can also be represented as the time derivative times the amount of time that it takes between the two bounces, right? So it's time derivative, dw per dt, times the amount of time between the two bounces, which is pi over omega. So now when you compare these two expressions, you already have the time derivative of the energy is minus omega over Q times energy. You plug it back in here, you can find the relation between the Q factor and this transmission coefficient, and you also know delta T is pi over omega. So when you put everything together, you've obtained the Q factor is given here, right? And obviously you recognize the same expression that we had in the transmission coefficient. So Q factor of the mode given by the numbers M and N, T, E, M, and N, would be actually given by this expression here. So SMN is the 0 and 0 of Bessel function of the order M. That also, of course, influences the field pattern of the mode and everything else. And theta I max is the critical angle for total internal reflection at the interface between two media with certain refractive indices. So that's, again, the upper limit on the Q factor, you know, because this takes into account only one thing happening in the system, which is imperfect confinement by total internal reflection in the radial direction. Of course, there will be imperfect confinement in the vertical direction, there'll be absorption loss, but this will still give you the upper limit on the Q factor, because if all other loss mechanisms are not present, this one will still be present. So that if all of the other ones are eliminated, this one will give you upper limit on the Q factor. So let's just analyze this expression and then calculate the Q factor for our microdisk that we designed previously, right? So conclusions from this expression are that Q factor would increase as SMN increases. SMN is the N0 of Bessel function of the order M. So if that 0 increases, if you go to larger numbers, like larger orders of Bessel functions and so on, if you increase the zeros, Q factor would also increase. If you go back to what relation is between Bessel function, 0 of the Bessel function, and also wavelength of the mode, this is the expression that we derived previously from the boundary conditions. And we found that the ratio between the radius of the disk and wavelength of the mode, lambda mn, so this is the free space wavelength, would be related to 0 of the Bessel function using this particular expression here. So as you go to larger SMN, that means that the ratio between the radius and the wavelength of the mode would increase also. Okay, so that we already discussed that before. We said, well, if I go to higher order modes, which means also larger SMN, then the wavelength of the mode becomes smaller relative to the radius of the disk. Or in other words, if I would like to my mode to operate at a specific wavelength, 1550 nanometers, but I would like it to operate in higher order mode, that would mean larger SMN, or also mean that you have to fabricate a disk that has a larger radius relative to the wavelength. But going back to the Q factor, if wavelength is small relative to the radius, if you have large diameter disks, SMN would also be large, and upper limit on the Q is large. If you have a lower order mode, let's say radius of the disk and wavelength are comparable, then SMN is smaller and Q, upper limit on Q is smaller. Which is why when you actually go back to paper that we discussed on kind of record values for the Q factors, those are obtained for large orders of azimuthal numbers of the mode, right? So these record values are measured for, I believe, one of these modes. I guess it's around 30, 31, 32. They're kind of similar. So it's a large azimuthal number of the mode. It's not something that's measured for m equal to 2. And there will be other things going on for small azimuthal numbers. There will be some more radiation in the vertical direction and so on. So the record values of the Q are obtained when you go to larger order modes. That's an important point. So going back to the disk that we already designed previously, this is the Q factor expression. Going back to our 16-1 mode, okay? M is 16, N is 1. S 16-1 is equal to 21. That's the first zero, Bessel function J16. And theta I max you can find from as an angle whose sine is 1/2.7, right? Because remember, we're solving this in two-dimensional geometry. We're neglecting everything else. So we're actually solving this using effective index approximation, refractive index, because in the effective index approximation, it's a two-dimensional problem with refractive index 2.7, right? So a critical angle is angle whose sine is 1/2.7. You can plug that back in here and you obtain that the upper limit on the Q factor is 200,000, okay? So if you build this system, your Q factor is most likely going to be smaller than 200,000, because there'll be other things going on. I mean, there will be other losses in the vertical direction, absorption loss, and so on. But this is telling you that you will not see Q greater than 200,000. You can find more accurate estimate on Q by running three-dimensional numerical analysis for this. I mean, for example, from finite difference time domain method, you can calculate Q factor exactly, and it will be smaller than this. But you know, when you make a practical system also, there may be other things. I mean, if you have any scattering in perfect surface, roughness on the surface that will scatter more light, if you have absorption as they were talking in that previous paper, if you don't do surface treatment, it will be smaller than this. But in any case, I mean, this kind of small, simple expression is telling you that if you want to build a Q factor resonator with Q factor of million, you can't operate in 16-1 mode. It's not going to work. Okay? Any questions? For this particular refractive index and so on. So a few additional things. Sorry, I'm just checking. We have a couple of more minutes. Okay, we can actually go through this one. So a few more things, right? So we discussed microdisks, and there are also other geometries, and you can use exactly the same expressions that we derive for those geometries. Often in modern systems, you will not really see microdisks, especially sitting on pedestals. I mean, because that's not a very robust geometry. Generally, people would use micro rings, which are the same as disks, except that you cut out the central part, right? And they would, of course, they don't have pedestals, so they have to sit on some low refractive index material that would support them. So here is silicon on oxide micro ring, for example, and this operates. And so now my question for you is, how can you use a solution for microdisc in order to analyze modes of a micro ring? What would be N here?
Well, if N is equals to 1, it would be pretty similar, right?
Exactly, N is 1. Exactly. So that is another motivation to work with micro rings, is because when you actually go back to microdisc spectrum, and I'm sorry for clicking one by one, that's the fastest way of Zoom. If you look at this spectrum here, if you constrain yourself to N equal to 1, then you have larger free spectral range. There are all these modes with the larger N are not there. And that's good because it's easier to reach single mode regime. So by cutting out the central part, you are forcing the system always to operate in N equal to 1 regime. And that's good. You have larger free spectral range. You have these modes that are preferable, have smaller mode volume. You can easily couple to them from the outside. But solution is the same as N equal to 1 M modes of the microdisc.
Could you explain again why is equivalent to N equal to 1?
If you solve it exactly, it's not completely the same, because of course there is some field outside, but modes are still expressed as the modes that would have certain azimuthal number M, which would describe the number of zeros that you have around the edge of this ring, right? And then n is equal to 1, and then m, it would be cosine m phi, again, dependence in that direction. But this one lobe that you have here would basically be also represented as the lobe of the Bessel function. Not exactly, right? Numerical analysis would be the best, but they're approximately the same, because the ring you obtain by basically cutting out the central part of the disk. So some overlap of the field with the outside region would change the field profile depending on how thick the disk is. But if you have like larger width of the disk, then it would be probably pretty much the same. Okay, and in this case, you're coupling in and out from the waveguides, right? So there is an input waveguide and the output waveguide. So here, everything is in integrated geometry on the chip. So let's say if you scan the input field here and you look at the output port, when you hit the resonance here of the ring, you will see minimum transmission to the output port. So what is happening? Which basis would you use to solve this problem? Would you work with cosine m phi and sine m phi or something different? Propagating modes are better, right? E to the I m phi minus omega t. So you have clockwise and counterclockwise. So my forward traveling field on the input port actually here excites the counterclockwise mode, right? It's not going to excite the clockwise mode. And then I also designed the system so that this counterclockwise mode is dropped completely at the output port. And of course, this depends on the design of the system and overlap within the waveguides and the rings, so you have to be careful, but people can design the system to have nearly perfect efficiency of transmission to a particular output port. So this is your input port, this is your output port. There is nothing going on to throughput port and also this additional fourth port of the system for the right design. And next time we'll see how you can actually operate these rings also in the active configuration, where you modify their refractive index so that you can modulate transmission to the output port, which is useful for building modulators. So we'll pick up from here next time, and then also discuss microspheres and microtoroid geometries. Any questions?
Can you go over again why there's loss when the angle is even greater than the critical angle when it bounces off the side?
Because critical, the analysis that we had in class, which tells you that you have perfect total internal reflection in the system where you're in the ray optics picture, right, when your angle is greater than the critical angle, was the analysis that was done for planar interface and for plane waves, basically, right, which have only one specific K component. If you look at this system that we're analyzing here, first, you have a curved boundary, right? And you have some beam that has a finite extent in the cross section, right? So if it has, if you have your localized beam that is bouncing here from the interface, first it would have a bunch of different K components, right? It's not really just a single K component. It's not a plane wave anymore, but you have to decompose it into a bunch of plane waves. And the other thing is you have a curvature on the interface. So it's not a planar interface anymore. So when this wave with finite extent, even with a certain K vector, 1K vector, hits the interface, depending which point of the curved interface it hits, it would hit it locally with a different angle relative to the interface. Do you see that? Right? Yeah. Okay, thank you. So we're a little bit over time, so let's stop now and I'll see you folks next Tuesday. Thank you. Bye.
Thank you. Goodbye.
Bye-bye.